Started the recording. Let's start first of all where we stopped last time. So what you see here is actually what we call a seismic section. These data were acquired on a marine in offshore, and that's very evident from the column you see. There is no reflections, nothing very clear. We're on these shallow times from 0 to 0.2 milliseconds. The y-axis is time axis, most often in seismic reflection data. And we call that time what? Two-way time. That's the time it takes for the energy to go hit an interface and get reflected back. So the most prominent or strongest reflector is what? What do you think is the most prominent reflector there? That's the seabed. Am I right? This is the seabed. The reason being the acoustic impedance, the difference between the acoustic impedance or contrast between the acoustic impedance of the water column and the underlying sediment is so large, it will produce large amplitudes. The reflection is so strong. So we'll get strong reflectors. Additionally, you see other features. One of the clear features is this erosional surface. That's an erosional surface. It's not flat. It's very undulating. It means that could be an erosional surface. Another thing, I read bright spot. This is a bright spot. This is gradual stratigraphic change. What I see, my reflectors are dimming, are dying out. They're so strong, and after some distance, they die out. The amplitude gets to 0. This is called the bright spot. Why it's happening? One of the reasons could be that there is hydrocarbon. When the rocks initially deposited, they had a different physical property. After some time, after deposition, maturation of hydrocarbon in the source rock, they start migrating to the reservoir rock. That's a reservoir rock. It can accumulate oil. The oil will be catched up here, will be accumulating in this zone. So why it's so clear? Initially, the acoustic impedance between these rock layers, upper one and deeper ones, was almost the same. But the oil accumulation lowered probably or increased the acoustic impedance. So right now there is strong contrast between the overlying rock and the rock where hydrocarbon is contained. That will produce for me what I call bright spot. It's a bright spot. So if someone asks you, where should I drill? Where is a possible place to drill? I will. Is it here? Is it here? Is it here? That's true. So this is a sort of oil accumulation. There are other candidates, other possibilities. Collectively, we call them direct hydrocarbon indicators, DHI. We can directly indicate whether there is hydrocarbon from seismic sections or not. For example, that's one case. What geologic features you see? What are they? These two things. What kind of faults? Anticlines. And there are anticlines. These are what we also call four-way dip closures. Four-way. It's closed. The dipping is closed from all the directions. So they are in 3 distances. These folds are dome-shaped. So the upper layer, the layer up above, what this washed out, the white characters, what do you think are they? What rock type could they be? Huh? Kapok. That's a kapok. That's a sealing rock. That's a rock of low permeability, low porosity. Oil cannot go through or leak through these layers. And that's the reason there is, what could this be? Accumulation. That's the reason these signatures, you see, there could be accumulations. What I see strong reflectors. It means that there is either gas or oil. And I also see something very interesting, a flat reflector. A reflector that's straight, that's horizontal. What could it be? That's true. That's a contact, not necessarily water. A contact, when I refer to a contact, fluid contact, means that above, in the upper zone, I have gas. Beneath the gas is either oil or water. How hydrocarbons accumulate? The reservoir itself initially has water. Either oil or gas replaces the water there, original water. You cannot replace all the water. There is a water, we call it in petroleum, connate or irresidual, yes. We call it connate water or irresidual water. And it could be 20%, 30%, depends on many things. Imbibitions, and depends on wettability. I don't want to go further away because that's another topic, it's not geophysics. Anyway, what you see there, that's a flat reflector. That indicates probably there is a fluid contact. And we know that most of the fluid contact are flat. It's impossible to see a fluid contact that's inclined or dipping. That's a fluid contact. So if someone's asked you, where should I drill? Without questioning, without thinking about it, these are two possible candidate locations, 1, 2. This is another type of a structure. Who could tell me what kind of structure is this, geologically? What you see there? There is a fault. So here what I see, that's a fault. Geologically, if I try to make schematic diagram of what I see there, it could be resembled as such. I had a fault, and this is the same layer. That's, or the opposite, sorry. Yeah, that's true. That's the fault. This is a reverse fault, whereas this one is a normal fault. So if someone says, where I can't find oil, you can find oil accumulating in the footwall there. The migration will migrate from some source rock and it accumulates here. So this could be a kind of a contact, fluid contact, and the accumulation is happening somewhere here. Provided that the oil or gas is not leaking through this fault. One possibility is that the fault itself is sealing. The other possibility, the overlying layer, this layer, all of it is a capoc, is a seal, a shale. Shale has low permeability. All of this is a seal rock. That's the possibility. So what we have strong reflectors. You see there? This flat line thing, the red line, is a possible fluid contact. That bright red line we see there is a possible fluid contact. Someone asks you, where should I drill? Is that place a possible place or right place to drill? Nope. Is that? Yeah, that's true. By the way, have you heard of Fahoud field? It's a field in Oman. They missed the field by just few meters, 50 meters or 100 meters. They missed it like that. The next time what they used, Initially, they were using mapping technique, geological mapping technique, to bring the possibility that there could be oil there. However, once they did seismic acquisition, they found that they missed the anticlinal feature because the whole rock was offset by a fault. So the next time, once they did seismic acquisition, they drilled the exact where the oil accumulation is. And up until now, there is hydrocarbon production from the same field, Fahud field. This is another data from North Sea. Again, I see the same features. An abrupt change in the reflector strength. Strong reflectors then washed out, white reflector. White is meaning that there is zero. So in terms of colors, if I draw the colors, red probably depends on the standard you are using. Is it American or European standard? Red means strong reflector, and high reflections, whereas black means a negative strong reflectors and moving from a soft rock to hard rock. That's at least in what we call American SEG standard. So you are moving from soft rock to hard rock. The color would be indicated as a black using this color scale, red, black, white. Whereas the red will be indicated as strong reflector, positive reflector, and moving from soft to hard. Whereas white, it means, if the color is white, it means what? Zero, and almost in the same rock. There is no reflectivity. Most of the energy is transmitted to deeper layers. This is another case here. So many cases. All collectively, we call them direct hydrocarbon indicators. We also use seismic data for risk assessment. In PDU, they are using another technique called Microseismic to do risk analysis. For example, here, they kept injecting fluid deep into the ground. For many purposes. One of the purposes, we went to, right in Oman, they are trying to capture carbon dioxide and store it in what we call Omanophyolite. I think if you reduce the accumulation or the percentage of carbon dioxide in the air, we can reduce back the temperature of the earth. So this is why they inject fluid into the rocks, deep in the rocks. But there are many possibilities or many scenarios where there was an inactive fault. Once you induce or inject fluid deep into the rock, you might reactivate the existing fault. You might lubricate the surface, the plane of the fault. And if this is a tectonically active place, what could happen? What do you think could happen? Earthquakes, yes. So we might see earthquakes. So these are seismic sections, and they found out what is the reason why there were small earthquakes. This is in Europe. That's a case from Europe. There was a fault, long fault, which went inactive for several periods, but once they started injecting back the fluid lubricated this fault plane. And the people started feeling small-scale earthquakes. Some of them were damaging earthquakes. So in terms of activity, we can have such sections. That's a small section. The depth is probably 50 meters, 20 meters. That's the source. In that case is a hammer. Hammer cannot penetrate very deep sections of the earth. This is another source, mini size. Mini size is what you raise a weight and drop it. It goes to 600, 1 kilometer, whereas vapor sizes, dynamite, they can go up until 6 kilometers, 7 kilometers, 10 kilometers. So these are in kilometer. Why they are not into a time domain? Why I'm referring back again now, depth domain. Why they are not in time domain? What is the initial x-axis domain? It's time. Am I right? So why right now I'm showing them in depth domain? What do you think? What's your name again? Ammar.
Because you are talking about the strength of
No, again, these are seismic sections. These are seismic data.
the
The size.
How long it will go?
Hmm?
How long it will go?
So
Depend
I just arbitrarily assign some numbers here, depth numbers. يعني عشوائيا حطيت بعض الأرقام.
depend on the source of the.
But why I'm displaying them in depth rather than in time?
Time doesn't tell us.
Huh? Again, what's your answer? I'm interested, but how? I just arbitrarily change these numbers which were originally in time and make them in depth? No, there is a process called depth conversion. In geophysics, they try to convert this data from time domain to what domain? Depth domain. This is a whole topic. Students studied in the other course, applied one. So don't be astonished. Oh, in the previous sections, all the y-axis was time, whereas right now I'm finding them in depth domain. This is a process we apply called depth conversion to convert the data from time domain to depth domain. What we need? What is the information missing we need to depth convert? Velocity. Yes, that's true. We need velocity. And that's the reason velocity is very important. And one of the process to get velocity information is CMP analysis, common depth point, or CDP, or common midpoint analysis. By then, we almost conclude this chapter. So far, I was showing you 2D sections, whereas the Earth itself is a 3D, three-dimensional. Nowadays, the companies are acquiring data in 3D. So what you see, these are 3D seismic sections. And the main difference is that what is the interesting thing, so in 2D domain, if I assume that this is a reflector, that's how a reflector in 3D is, whereas the line I'm acquiring the data is that. So if it's dipping something like that, it has a dip like this is what? The seismic line, 2D seismic line. That's the surface. It's dipping not in any orientation with respect to the acquisition line. So it's an arbitrary, it's not either parallel or orthogonal. It's not parallel, the dip angle is not parallel to the 2D line. So if it's parallel, that's good. You will get the maximum depth. If it's not parallel, that's so bad because the reflection will happen not directly below the source and receiver. So this is the line. The source and receiver are in the same line. We assume the energy is coming directly from below the line, which is not always true. It will come from the shortest path. So the energy goes hit side and reflects back. So if you are acquiring 2D data, you will miss this information. You will lose this information. You cannot apply 3D migration. You will be constrained only to 2D migration. So the dipping you are correcting for depth is not accurate. Whereas in 3D data, the data are more accurate. The only caveat is that comparison between 2D and 3D is what you think. Why we don't go right away to 3D? It's expensive, time consuming, that's true. It's very, very expensive compared to 2D. 2D you can acquire it in very short time, whereas they spend months and years probably acquiring 3D data. So these are 3D data. The interesting thing, I can take a section in any direction. So you think about it like a cake, a piece of cake. How you can cut the cake in whatever orientation you want. Horizontally, vertically, in any direction, arbitrarily. That's the same case with 3D seismic data. So what you see this line, that's a cut. This is another cut. And that surface you see, it's called time slice. It's called what? Time slice. Why time slice? Because the data originally in time domain. The y-axis is time domain. So if I cut my cake, what I assume is a cake, horizontally, so I'm almost showing certain time value. Another interesting thing is this surface slice. That's a surface slice. So what I mean by surface slice, let's go back because that would be easy. So what is that? Who colored this thing? Were they initially, once you finish the acquisition and do the processing, you will see these lines? No. Who did this line? Who mapped these lines? Geologists. Yeah. This is the process of interpretation. So in 3D, that's a 2D line. In 3D, that's one line. You do the interpretation. You move them, another line, another line, another line. What you can produce then? A surface, a 3D surface. You can produce a 3D surface. So these are different geologic layers. I'm trying to interpret. The geologists interpret. Nowadays in computer, you just by mouse, you can go through them very fast. Whereas in the old days, they were doing this process interpretation manually. They get these sections printed out, on them, put them on a table, on a disk, and start interpreting, which is a very tedious process. Nowadays, things are computerized. You get these things into computers and start by mouse following a certain interface, a certain layer. That's the process of interpretation. This fault is also an interpretation. So if you do this interpretation on several sections, on several lines, you first start drawing them in parallel lines, then that's what we call inlines. Then we try to interpret in the cross line. We can build a net. And if I interpolate it, I create a surface similar to what I see here. Because this surface is cutting through the seismic data. And what are seismic data? What information you get? What is this data originally? These are amplitudes. Strong amplitudes, small amplitudes, large amplitudes, zero amplitudes. So amplitudes get larger. The larger is the reflection. The stronger is the reflection, the higher is the amplitude. These are the different amplitudes. So I can extract, if my surface is cutting my some seismic data, I can extract amplitude information along the surface. I cut or I extract amplitude information along that surface. يعني بالعربي أفهمكم بطريقة مبسطة أن إذا عندي surface يقطع شيء مكعب، أريد أعرف المعلومات اللي على surface اللي على surface بالضبط، أو الافريج، أخذ تايم أعلى وتايم أقل. I take the mean values. So I get usually very interesting features. So what we are getting here, what could that be geologically? إيش ممكن يكون هذا geologically؟ Huh? What? Yes, you're right. Yes, what? Alluvial system. That's an alluvial. This is wadi channels. كان وادي ماشي كذا وكذا شعاب يرجع. Alluvial channels. So this is a wadi channel we see. So along inside those channels, the reflection is high. Away from them, the reflection is low. That's a surface. We extracted amplitude information from them. It's very interesting. So we'll stop here because the next one is 3D acquisition. You don't need to cover it. The last slide, I might remove it and re-upload the same one, the same slides. And for the reading, read these parts only. from 7.9 to 7.12. Don't study what we call sequence stratigraphy. There is a part called seismic sequence stratigraphy. That's a bit advanced, I believe. So seismic sequence stratigraphy, you can tell from seismic data how the deposition environment was, how rocks were deposited, what was the first layer, the second layer, and so on, which is very interesting. So let's move to the next chapter. Try to cover something from the next chapter. That's seismology chapter. Let's move to gravity chapter. First of all, gravity is a passive technique. We are measuring the naturally occurring gravity field of the Earth. If I ask you, have you ever made any measurement of falling body in physics? Physics 1 or Physics 2? So what is the constant value of G? And they probably sometimes assume it, how much? 10 for simplifications. Do you think, is it true? What is the accurate value? Is it varying from one place to another place? That's true. It's varying. So this is what all about gravity technique. We are trying to measure those small variations. They are so tiny, we need very, very accurate or precise instruments, very sensitive instruments. And those measurements are in the order of 10 raised to power minus 6. Those small chains are in the order of how much? 10 raised to power meter per second squared. That's the unit of usually gravity. We say meter per second squared. That's the measurement of. So do you like Newton or not? That was Newton. The apple dropped on his head, so he came up with this equation. And we are trying to use the same equation. Gravity measurements are all based on the same equation. It only differs how we measure it. How we measure this little force, that force. How much is it? That force could be equated to what second law of Newton says? M? A is what into this thing? Acceleration is which is what? G, the gravity force. So it's mg. So we are trying to measure that m. We are trying to measure that little g. mg. G is the gravity force. If I type mg, m, what I can cancel? mg equal this equation. This part, the left, the right hand side. M and what? M1 or M2? If we are referring to the force between me and the Earth. Let's say this is the mass of the Earth and that's the mass of some human. So am I removing the mass M1 or M2 if I equate this one? mg equal g m1 m2 over r squared. That's the radius of the Earth. We assume that's the radius. So which one it cancels? M1, let's assume that this is mass of the Earth. That's which one it cancels? Is this one equated with this one or this one? Again, who is with M Earth? Who is with M Earth? Raise your hand. Who is with M small? And the rest are not sure which one is it. So it cancels actually with this one. That's how is it. And that's the reason Galileo long time ago said if he went to the Tower of Pisa, you know where is the Tower of Pisa? Pisa Tower? It's a leaning tower in Italy. He started dropping different objects of different weights, and he came to the conclusion the time it takes for the object to fall to the ground is not dependent on their. That's true. I don't need to go back. This has been studied, I believe, in physics back in schools. So the time it takes to fall two different objects, it does not depend on their weight. That's true. So G is the same force whether you are exerting it small body or large body. It's dependent on distance, how far you are falling it from. So that's the subject. We try to figure out what is this G. We just say that's how much? 10, which is not exactly true. It slightly varies. Those variations are due to many factors, and one of them is geological variations. Geological variation in the subsurface. So if there is a large accumulation, let's say a large sphere of gold. Gold is so expensive now, right now. So if you get a gold, that's a treasure. And I'm trying to measure this delta D. What you will observe on that, if you are taking measurement on top of that ore body, gold or gold deposits, an increase or decrease in the value of G. Huh? So let's make it, خلينا نقول I'm taking measurement. There is a huge, large deposits of gold. And I'm taking measurement one here, one here, one here. Measuring what exactly? What could I observe? Could I observe something straight and 10? Or could I observe something like that? Or I could observe something like that. 1, 2, 3. So assuming that this is gold. Huh? 1, 2, or 3. Could be 1 or 2. It depends on the host rock. This is the. So if the host rock is having a rock of density larger than the gold, if the density of the host rock, this rock, is larger than the gold, what do you observe? 3. If, let's assume this is a sedimentary rock, homogeneous sedimentary rocks, I'm trying to find gold, so this value will get the first line. In our measurements, before I go dig deeper, in our measurements, we are not measuring the absolute value. يعني 9 point long number. No, that's not true. We can't, but it's so difficult. It's very difficult. It's not practical. For reasons I will discuss soon. We measure only differences. We establish a station, يعني هذا الريفرنس، هذا البيس. نشوف الفرق بين هذه النقطة, this point, base station, and other points. That's what we usually do in geophysical or gravity surveying. It's possible to measure the absolute, but it's hard, it's time consuming, it's not practical, it's very expensive. And I give you an example, how expensive it is. So, Ministry of Defense, they have a department called Surveying Department. Ministry of Defense in Oman, they have a department, they do survey. And once they approached us, they said, we want to know a point, we need to find a point where we want at that point to determine exactly what is the value of gravity. Exactly, precisely. They kept measuring at that point for 3 days. 3 days to establish absolute gravity. Precise value of gravity is inside the SKU. The point is inside the SKU. But it took them 3 complete days. So if you want to cover a large area, and you want to take hundreds or thousands of points, imagine how much it takes you. It takes you your lifetime, your children's lifetime, your grandchildren's lifetime, to just finish acquiring one small area. It's not very practical. Whereas they just measure the difference, the variations. So how it could be done? That's the topic, and I just discussed a lot of things when we are measuring regarding this slide, this specific slide. So I discussed so many things. First of all, gravity force is the vertical force. There is no gradient force like magnetic. Gravity always, at least the gravity of the Earth, the force between you and the Earth itself is the vertical force between somebody and the Earth. You, which is pointing directly to where? To the center of the Earth. It's pointing directly to the center of the Earth. That's the Galileo said that we just discussed these things. So that's the gravitational force, Newton's law, first law. We equated with Newton's second law. Small m will cancel. We are left with this equation. And we're trying to measure little g. We are trying to deduce little g. But not precisely the g itself, variations in g. So following this formula or this equation, trying to adhere to it, if we adopt two different objects, is that true? Would they follow like that, fall like that, if we ignore the resistance of the air? They will fall rather this way. So the variation in G, there could be two different factors. One of them is the rock, lateral change in rock. I'm having denser rock in one location than the other rocks. Gold is a dense. Iron is dense. The density of iron is 7 point something gram per centimeter cubed. That's the density unit. Could be due to topography. What happens if I climb a mountain? What happens to the value of G if I climb a mountain between me and the Earth? It will decrease based on the Newton's law. The R increased. So if I climb a mountain, the R increases. And it increases or decreases whether I'm taking measurement along the equator or the poles. So where do you think the gravity value is larger, along the equator or the poles? Larger. Poles or the equator? No? Yeah, because the radius, because the centrifugal force. It is rotating along its axis, so it's trying to pull things away from the center. So there is another force which is centrifugal force. The force of the direction of centrifugal force is opposite to the gravitational force. It's pointing outward, whereas the gravity force is pointing toward the Earth. So topography, another thing, mantle blooms. It's somehow mantle blooms are geological features too, but mantle blooms are happening so deep, very deep. You know what's mantle blooms? Anyone not aware of mantle blooms? I believe you studied them in Geology 1 or probably Geology 2. So this is the Earth. That's the crust surface. This is the inner core. So this is the inner core, the core itself, and this is the mantle. The mantle is so hot, sometimes it raises blooms of magma, hot magma. We call them mantle blooms. So they have a different gravity value than the surrounding. This is not mere geology, am I right? It's not something I try to find in mere geology. Could I dig and drill for these features? Is it possible to? So they pose no interest to me as a geologist or exploration geologist. Mantle blooms, topography, other external factors. Could someone tell me what is an external factor which can affect the value of gravity? Tides? That's true. Tides. Perfect. tides. يعني have you heard of tides? موج مدول. Yes. So the sun and the moon are pulling also the earth. So the G value is changing because of the tides. Is it a geological interest to us? No. Did I explain these things before? Yes. In the introduction chapter, do you remember when I said gravity also get affected by tides? And we try to remove, we are interested among all of these three. Which one is of interest to us? Which we? First one. First, we are trying to change lateral chains. That's of interest to us. We try to remove the other features. So in the lab, next lab, you will be doing corrections, gravity reduction and corrections. So let's take some examples. That's the gravity value, and these are some constant, G constant. This is the average value. How we can measure? If someone asks you what is the mass of the earth, based on this equation, could it be measured practically without using satellite images? Or without making, could we measure the mass, what is the density of the earth? Yeah, it's possible. It's possible based on this equation. So we know already G, using some experimental lab experiments. You already know the little value of little g. Little v, g could be known by dropping objects. Am I right? Timing them, how much time it takes for the object to fall to the ground. That can easily be known. R could be known by taking some measurements. The first guy who said that the earth is circular feature was a European guy actually. He made measurements of how long are shades of buildings at the exact time, 2 different places. So he made measurements in Scandaria and one in where those pyramids are, Luxor, the name it? Am I right? In Egypt, they made the measurements. So he found that the same time, exact time, the shade is longer if we move away from the equator. The shades of the buildings are longer if we move away from where? The equator at the exact time. So using some calculation, he determined what is the radius of the earth, this value. Right now, because of the satellites, we can precisely tell what's the value of R, radius of the earth. So once knowing these measurements, or at least for today, we can precisely measure the value of capital M, the mass of the earth, which turns out to be that much. It's big mass. That's really, really huge mass. 5.97 times 10 raised to power 24. So this is the mass. That's the mass. How we find the density if we know the mass of something? Volume. What was that? So volume. We can tell by the volume. So it turns out the density of the rocks, usually the average value is 5.5, which is a bit high. It's large. Most of the rocks on the surface are in the range of 2 to 3 megagram per meter cubed. Megagram, or the same if you convert them to gram per centimeter cubed. Gram per centimeter cubed. So the range is 2 to 3. What is the density of, let's say, average density of limestone rock? 2.7, 2.8. Sandstone is 2.7. What's the density of water? 1, that's true. Density of water is, pure water is 1. Density of saline water is little bit larger than 1. 1 point something, some value. So why this is so high? Because the interior side or the core of the Earth is made of iron, which is 7 point something. The average value, the total average value then comes out to be 5.5. So these are values of a range of different rocks types. So they change because of many factors. One of them, their age, their compaction, their type. Which one you think is denser, sedimentary rocks or igneous rocks? Igneous rocks are denser. So in terms of density, igneous are the most denser, then metamorphic, then sedimentary rocks. So loose sand, unconsolidated, they are within that range. If we go deeper, sedimentary rocks, they are within that range. For example, igneous rock, they are getting larger. Ore body, galena, pyrite, magnetite, they are very, very dense. They are pure minerals probably, or ore bodies. Galena is a mineral. Pyrite is also a mineral type of magnetite is also a mineral. They are very, very heavy. So they vary for many reasons. The source, whether they are having withering, unconsolidated, or consolidated. The deeper they are, the deeper the rock, the more compaction they get, and the denser they become. Another factor is their age. Another factor is dolomitization. For example, in sedimentary rocks or limestone getting dolomitized, dolomite is a little bit denser than limestone itself. Another important parameter is porosity. Porosity and also fractures, whether the rocks are fractured or not. Fracture, what they do to the rock density, you think? Will it reduce or increase? Reduce, decrease. So usually when we try to do gravity measurements, and the final objective, as I said, we try to measure variation, the difference from one point to another point. What is the difference in little g, small g, from one point, not the absolute value. No, I will say why we don't measure the absolute value very soon. But in general, we measure only the little g, the small g, small g, which is due to variation from one point to another point. That's the measurement we do in gravity surveying. So in case if you are having homogeneous rocks, would you get any anomaly, any variations? What kind of line you get? 1, 2, or 3? 2. If the rock is the same, if it's homogeneous. What about if the rocks are all layered horizontally, one on top of each other? And each rock has its own specific density. What do you think in that case? Would I get what kind of line? 1, 2, or 3? Same. There is no change vertically, or sorry, horizontally, from one point to another point. If I'm only measuring the variations, this value is going to be 0, not 10 something. I'm always subtracting the difference between some station, some reference point, and the surrounding, the difference. So it's always 0. There is no gravity change. Unless you do measure what? Absolute. The correct, which takes a lot of time. Unless you measure the absolute values. So if I measure the absolute value someplace and the rest of the area is 0, in some place I measure the absolute, it was 9.8. And the relative, I make a comparison between absolute. What is the opposite of absolute? What is this acronym or synonymous of, relative, absolute and relative dating. Have you heard of dating, rock dating? There are two types of dating. One of them is absolute, the other one is, and we can do also measurement, relative measurements or absolute. So keeping this in mind, because that's quite important, if I made a measurement in some area, and I found these are all my measurements, and I assume that the rock is homogeneous, what kind of relative measurement I get? What is the value of relative gravity measurement? What is? 0. That's 0. 0 because there is no change. Then we come and take measurement, absolute measurement somewhere here. What we do with these two different data? I have absolute at exact point and relative everywhere. I just يعني الابسولوت مثلا هذا الابسولوت let's say this absolute were 9.8. What is then the absolute here? Rest of the area. It's exactly the same as this one. 0, everyone 0 plus this value. It's just 0 everywhere the relative was 0. I add the relative to the absolute. That's how I make, I convert from absolute, so relative actually to absolute. And that's the reason we had a measurement here in SKU. So if I want to get the absolute value of gravity in whole of SKU, initially I made relative measurements. I should take my reference to that specific absolute point. الابسولوت بوينت اللي موجود هنا اخليه هو الريفرنس. انا عارف كم القراءه الجرافيتي بالضبط كم هنا. واخذ قراءه مناطق ثانيه وارجع كل شويه ارجع لل I say why we return. But that's the values. And one interesting thing, we measure a lot of properties of the earth. We said we measure velocity so far, we measure resistivity later on, we measure also magnetic susceptibility, what is the magnetic field of the earth, and that's density. Which of them you think has the smallest variation in the rock types? Gravity, that's true. And you see it's small variation, whereas in velocity it varies a lot. In the resistivity you will see the same rock, sandstone, has a lot of different resistivities. Resistivity could be 1 up until even 2000 ohm meter. That's the value of resistivity. So how we can measure resistivity? Let's take an example. This is a simple example. I'm trying to find not the absolute, but the relative. The relative change due to a different body in the subsurface. We assume that the earth is homogeneous. In this specific case, I try to find the extra or the excess mass of this body or variation in G due to this excess body. So the thing we need to know or recognize is how big is this feature is. What's the volume of this feature? I'm ignoring all the other measurements. So initially, we know that the geography or the value of G is capital G M over R squared. M, mass of whole earth. But no, I'm not interested in the mass of whole earth. What I'm interested in, mass of what? This body. This target body, not whole of the earth. Mass of this body. I don't know the mass, and the gravity value is not measuring the mass, it's measuring density variation. And how I can tell the mass? By the volume. I need to know what's the volume of the body. So let's take some simple measurements. That's the law of gravity. G equals capital G, constant G, mass of the earth over the radius of the Earth. I'm not interested on a whole absolute G. I'm interested on only change due to this body. So I'm interested right now, instead of R, I use the distance to the center of the body. And instead of whole mass, whole Earth mass, I'm only interested in change. That's what I can measure, change in density. I'm measuring change, relative change in density, change in masses. And we know a mass is equated to volume times density. I'm measuring what? Change in density. So let's assume that the change in density between the surrounding and this body is 0.3 megagram per meter cubed. Mega, not gram. Megagram per, and that's the depth to the center of the body, and this is its radius. So we already know its volume. We know the volume from the radius. That's the conversions we do. So instead of R, we use D. And the other part is what? 4/3 pi R cubed is what? Volume times change in density. We plug in all the numbers. The numbers are given. That's the value. That's the change I get. The difference I get. So I assume that this is a positive. If I make a lot of measurements, one measurement at least, this measurement in the center, let's assume this is delta G, this is X, I'm taking a lot of measurements. The maximum one, the maximum 0.3 is here. If I take a measurement here, would it be, this is my body, would it be larger than 0.3 or smaller to the other sides? Huh? It will be smaller until it never goes to 0. It tries to go to 0. So that's the maximum one in the center. That's an easy thing to do. So what about if I take measurements here rather than on the surface, on the center? Let's make some small modifications, but before that, this is the value I get. That's the value I get, that's meter per second cubed. Squared, sorry, not cubed. How much is it? It's very small. It's not 9 point. Can I compare it to 9.8? Compared to that, this is nothing. It's ignorable. This is very small number compared to 9.8. This is not the absolute, that the change in delta in G itself. How much change in G between a measurement somewhere far away and C, and point C. I add how much to G? How much I add to 9.8? How much I add? This small number. Would it affect it? There is no effect at all. Almost did nothing. So, the density is large. That's true. There is a different body. So, to measure those small changes, we need to use, first of all, very precise instruments. We are interested in those changes. They are very important to us as geologists. They infer that there is a change in the subsurface. I'm encountered with a different body, a body of a denser material. So we don't use actually this unit, meter per second. We use a different unit. We call it Gal, in honor to Galileo. You know Galileo. Galileo is the guy who dropped different material and came to the conclusion that the two bodies will fall at the same time, irrespective to their weight. That's what Galileo came up with. You know what Archimedes came up with? Huh? Yeah, he put a body in the water. How much will be replaced? Buoyancy, somehow buoyancy, but he weighted how much a body can weight. What's the weight based on this formula? Yani? How much volume you replace of water? Anyway, so they use another unit called gal. 1 gal equals how much? 0.01 meter per second. Still, this is a bit large. Instead, they use what? Milligal. Milligal is smaller than gal. 1 gal equals 1000 milligal. And gal akbar. Milligal is smaller. And there is another unit, very common unit, they call it gravity unit. Gravity unit is still smaller than milligal. So 1 milligal equals 0.01 gal. And equals how much? 1 milligal equals how much? 10 gravity units. And that's the value in terms of meter per second cubed. How much? 1 milligal. Referring back to the previous value we got obtained from this equation or calculations. So we try to convert it to gal. How much gal we get? Milligal? 0.1, approximately 0.1 milligal. So we need an equipment that measures variation which are very small, smaller than even 0.1 milligal. We need very precise equipments that can measure small variations. Differences between one point and another point. What is the difference in terms of delta G? Using the same concept. We don't use R anymore. We are using only the distance between the measurement point and some target point. And what's the volume of that target point? So let's make some other measurements instead of directly measuring on the top. So we try to measure. That's how usually the measurements are done. We take profiles, transects along the target body. It could be 2D or could be 3D. We take a lot of parallel lines. So if I take a measurement here, this is what I measure. And the gravity is always measuring the downward, the vertical component of gravity. That's what I measure. Do you think this body here to the side, will it have an effect to the reading at P1? Will it increase the overall downward G? Huh? Yes, it will, because this is the original Earth. This is the original G due to Earth. This has some component. The force between this body, the direct force between this body and the measurement point here is F body, force body. That's F Earth itself. But this has how many components? Horizontal component and vertical components. So that small vertical component will add up to the overall. We try to measure it right now and try to find how much it could be. So we try to measure these small extra delta G. So let's assume this is the simplest measurements we can make. Yeah, that's how is it. For simple cases, we try to measure the change in mass. The change in mass, we are measuring the vertical. In this case, the net, the overall, because the center of the body is directly beneath the measurement points, the net delta G is equal to vertical one. So that's my equation. We already came up to this equation before. What about if I take measurement to some point sideways? Sideways, and there is a theta, an angle. So that was the original Z. Right now there is an R, that's the measurements. However, I'm not taking that measurement. Which measurement I'm taking? The vertical. I'm interested on the vertical. What is the difference between, right now, between the net and the vertical? Which one is the net? This one or this one? Which one is the net? 1 or 2? 2 is the net. Vertical is the one I measure. Can I get the vertical from the net using this, what you see in the geometry? How is that? Cosine theta. That's true. Perfect. Yes. Cosine theta multiplied by this value gives you vertical one. So multiply cosine theta by this net will give you cosine theta equals what? مجاور opposite على الوتر. So multiplying this cosine theta with this value gives you this value. And that's what we do. Cos theta multiplied by this one. Instead, right now we are using what? R. That's the distance to the center. That's what we vertical measurements. Which one you think is larger? This one, this vertical, or this vertical? The first one, because this definitely is larger, first of all. R is larger. That's one thing. And we multiply also by cos theta, which is less than 1. Anything less than 1, we will multiply it by that value. It will give you a smaller number. However, this is not a convenient way to measure. We try to simplify it. First of all, there are two relationships. Cos equals what? In terms of distances, cos equals Z over R. And we know R is equal R squared equal X squared over Z squared, plus Z squared. So let's do, this is my original equation. First of all, I replace cos theta. So it becomes what? Z over, add Z over, or multiply by Z over R cubed. Then we substitute for R. Instead of using R, we use what? This value, sorry. X squared plus Z squared. Raised to power of all of them, raised to power 3 over 2. That's my value. And that's how the calculation is. And we don't use M, delta M. We use density variations. We try to get density variation. So volume times density. So this is the final equations. Do you need to remember these equations now? So it's equal that value. Overall, this one is smaller than when you are taking measurement directly above the body. This is a 2D measurements. I'm taking line 2D. If I take measurements 3D, that's the same sphere. Let's assume that it's the same sphere. In 3D sense, I get some shape like that, the data shape. What I call this feature in geophysics in general? Anomaly. That's an anomaly. That's what you see, an anomaly. Is it positive anomaly or negative anomaly? That's a positive anomaly. That's a positive anomaly, assuming that the body here has a denser material. The density of this body is larger than the surrounding, the host rock. I get a positive. If it's opposite, I get a negative anomaly. The value you get here is in milligal. It's the difference in gravity between one point and another point. It's not the absolute value. It's not 9 point something. If it was 9 point something, it would have been a big, large number in terms of milligal or in terms of gravity unit. And 9.8 meter per second squared, you convert it to milligal, it's going to be very large number. So let's see how those anomalies will look like. There we have two different things. One of them, this is spherical targets or cylindrical targets. What could be spherical targets in geological sense? They appear. Have you heard of they appear? Huh? Salt, yes. Salt usually when it moves, it tries to push the rock above. It creates some features like that. So this is the salt because it's very movable. It tries to find the weakest point within the strata to push them, to break through them, to create such features. Salt appears. This shape is what sphere, almost like كورة كانت تطلع كذا. It's a sphere. Or plutoons. What are plutoons? Magma intrusions. Plutoons are what? Also magma intrusions. They are spherical shapes usually. So they give you an anomaly similar to this. One interesting thing in the anomaly, what happens if my feature or the target is closer to the surface? What is the difference between these three measurements? Solid line, dashed line, dotted line. The solid line is the anomaly due to which one? 1, 2, or 3? That's true. So what we observe, the closer the target to the surface, the steeper is the anomaly. That's one thing. The deeper you take the target, the more the gradual the change is. So I was saying, so you see here, this is a sphere, the anomaly due to sphere. It's hard, actually first of all, it's hard to discern between or differentiate between spheres and cylinders, at least in gravity and magnetic interpretation. So this anomaly, first one, solid line, is due to when the target was closer to the surface. Why is that? What happens to the R? It decreases. If R decreases, what happens to the force G, delta G? It increases. If I make the same, bring it deeper, move it deeper, what happens to the anomaly? It decreases. So these two are different objects. Cylinders are like, this is a cylinder, cylindrical features. What could be a cylinder? Tunnel. A tunnel is a cylindrical. Do we have tunnels in Oman? Anfaq. Yes, we do have just one which was recently opened in Dakhliya region. Am I right? Is it in Dakhliya or Sharqiya? So it's actually hard to distinguish between what feature produced the anomaly. And that's, we call what? More than one model produced the same anomaly. That's called non-uniqueness. Potential methods, gravity, these are potential methods, passive techniques, they are non-unique. More than one model can produce the same data. Can geophysicists do anything? No. You need to consult a geologist probably, bring probably will data, or use another technique. Combine gravity with seismic, combine gravity with resistivity probably. The same thing we see, that's the anomaly from cylinder. There is not much difference. Yeah, and I can produce the same anomaly if I bring this one, this body closer to the surface. I could produce the same body. That's what we call non-uniqueness. Another thing, there is no sharp edge, and the anomaly is gradually changing or decreasing. It's not like a break. Oh, this is the boundary between the object or target and the host. It's not like that. Let's take examples of different things. We have sheets, you have dikes, vents, they look like similar. A sheet, a dike, or vents, they give sheet-like features. So one interesting thing, if we take this line, what happens to the anomaly if I bring the target closer to the surface? The anomaly will become larger, sharper. It's large, sharp. So one thing is how close is the body to the surface. Another thing, how much is the contrast itself? How much is the density variation? When it's large or small? If the density contrast is large, the anomaly going to be large too. Another thing is, how deep is it? Is it shallow or not? Density contrast. How long is it? And what is the dip of the sheet? The inclination of the sheet. If I keep inclining it, what happens? It gets squeezed. You know what's squeezed? Becomes asymmetric. Becomes asymmetric. So the maximum value is always where? At the center of this sheet. At the center of the sheet. Is it easy to make such measurements? Can you tell me? It's not easy. It's not easy at all. People can come up with hundreds of different models. Still, all of these models give you the same results, the same anomaly. That's highly likely. You can't say seismic techniques or geophysical techniques are useless. Nope. Based on such data, they made a lot of analysis. They make conclusion based on this data. You should usually take the larger perspective, bring other types of information to the table before making conclusions. What about an infinite sheet? An infinite layer? A layer which is extending indefinitely. What kind of anomaly I get? I get a positive or negative anomaly, am I? Huh? I get the same. There is no anomaly. There is no anomaly, but I might get an increase or a decrease. The anomaly will be like that. 2 pi g delta density times thickness. Time thickness. The delta G will be calculated as such. There are two, these are the same, the density contrast in these two cases is the same. There is only one variation. One is deeper than the others. What you see? Which one is shallower and which one is deeper? Definitely the sharper edge, the larger anomaly is due to the shallower object. That's the deeper object. So this is what kind of fault? This is a strike-slip fault. That's a fault plane. Let's say that those are different rocks. They got offset. This is supposed to be continuous. This is another layer, continuous, but I'm looking from the surface. One rock, another rock, another rock. If you measure like that, starting from here, you take a line like that, would you observe something? Vertical يعني هذا كلنا نشوف من surface. آخذ قراءات. I will detect a difference if this density between this and this is not zero. If I take a measurement in here, a line like that, zero. No, there is no change. There is no change. Likewise, if I take a measurement here or here, it depends on what the density contrast between these two different layers. What if I'm taking a measurement here? Let's assume I'm taking a measurement here. In this specific case, I assume those layers are vertical. What if they are inclined? I'm taking measurement here. What if they are inclined? Would I get an anomaly or not? I make a simplifications. So let's assume this is a layer. This is a different layer. Here is I have a layer. It's vertical. If I take a measurement like that, this is a different density than the surrounding. This is how I'm measuring from the surface. Would I get an anomaly or not? Definitely there's going to be an anomaly. If I take a measurement here, would I get an anomaly or not? Not necessarily, but if it's inclined, then yes. Then I get an anomaly. So such faults, neither normal nor reverse faults, they might produce no anomalies. So this is an anomaly I produced. That's an anomaly in milligal. These two models, they are both entering the data. They are two different models. They produce the same anomaly. That's the original one I recorded from the field. I come back to the computer, to the office. I try to do modeling. So converting from data to models, what kind of from data to models. Yeah, that's inverse. From models to data, that's forward modeling. Yeah. Bringing data, converting them to models, that's inverse modeling. So there are many different techniques how we do inversions, but the simplest right now is doing computer integration, advanced numerical analysis in computers. I don't want to go to that point, but basically in one of the lab, not next lab, the other lab, the thing you will do in gravity, because the modeling in gravity and magnetic technique, it's almost the same. I will give you a software. What you will do, similar to the Coral Draw. Have you ever used Coral Draw? Inkscape? Adobe Illustrator? None? Yes. You create shapes. You create shapes with a Coral Draw, other one. So this is similar. You start creating a shape, that's a line. Then you create this body. You continue with these lines. The only difference here, you assign each body what? A physical property, density. And then with a simple click of a button, you ask the computer to do what? From here to data, what do you get? From model to data, what's that? Forward. That's what you do. So you create this model, you ask the computer to produce for you the data. This data which are produced from the computer, using forward modeling might be different than the original you recorded in the field. So if they were different, what do you think about your model? Do you honor it? You need to update it. You need to update it. One way of updating nowadays, instead of wasting your time, there is another button, then you just click it, you say, oh, make an inverse modeling then. What inverse modeling then? You got data, it tries to match, decrease the difference between observed and calculated. Calculated is the one you produced after you modeled. So it starts inverting. These things will automatically update. But you need to put some constraints. You say, okay, only change this layer. Don't change the other. Software will change only this layer. Or else, if you don't do inversion, what you can do, manually, you can change it. These are nodes, and one point here, another point here, another point here. You can pick one point and start dragging. Once you start dragging, what you observe up there? A change. You keep dragging, changing, until you find that there is a match. What is the best way to make a model? What could I add to make my model perfect? Huh? Ish? Well, that's true. And what kind of log data we could incorporate? Have you heard of density log? So if you have a well and you have run density log, so along the well you have the density values. You start modeling from there. You start, okay, this density this well, this is the well. I know exactly what's the density along the well. Away from the well, I try to guess. So one way to decrease this uncertainty or remove this non-uniqueness, come to one conclusion, one model rather than millions of models, is bringing what we call geological data, well data. Incorporating, if you have one well, at least along the well, what's my certainty? From 0 to 100% along the well. How much am I certain about my data along the well? Almost 100%. Away from the well, the uncertainty increases, the certainty decreases. Your confidence of the data along the well is high, away from the well is low. That's somehow we do modeling. And you will use, for the time being, at least for gravity corrections, for the two labs, one of the lab is on gravity corrections, you will be doing corrections or what we call reduction. Because reduction in gravity technique is very complex, whereas much easier in the other method we call magnetic. Shall I stop here? No, shall we move a little bit more? Because I want to start covering something about corrections, how we do corrections. So how we measure gravity? There are many techniques. One of them is, what we do? Dropping an object. Dropping an object. We keep dropping an object, which is not an easy task. That's what have been done by Galileo. And we try to time how much time it takes to fall to the ground. And that's the equation we follow. 2 distance over time squared. So we know exactly what is distance, but it's hard to measure precisely the time. This gives you the value of G. What G is that? Absolute. That's the absolute G. If you use this technique. So are we using in our techniques or our measurements this type of apparatus or this type of methods? No. This is tedious job. It's hard. There are apparatus which can detect these type of G, but they are very bulky, large, as big as trucks. So you cannot move them easily on the field. And they take time. They take time measuring. That's one way. The other way could be pendulum. The other way is pendulum. You measure the period, how much the pendulum takes one period, ignoring any resistance. That's the equation, 2 pi L. What's L? The length of the pendulum. The length of the pendulum over G. So our objective is to find what's G. What G you will get if you use this technique? Absolute. That's true. That's absolute G. Which is not practical actually. It's very bulky operators, it's time consuming with it. And the absolute gravity we measure it here in SKU, we use such operators. It took 2 complete days to just get 1 point, absolute value. We use something else. We use a spring. A spring tied to the mass. That's what law is that? Back in calculus 1 or physics 1, what law is that? Hooke's law. That's Hooke's law. Hooke's law. Hooke's law is mg, mass times g. So if there is any extension, any small extension, it means what changed? With the mass changed? It's the same mass. What have changed? Gravity plus delta G. So that's delta G. Is it absolute? I'm already not measuring the absolute here. I'm just measuring some reference. So I measure it at some point first. At some point, I take that point as the reference point and move to other points. Any change, decrease or increase, that will be incorporated or interpreted as change in small little g. This is a bit hard to maintain. It will bring a lot of errors. Instead, they use a beam attached to an arm. Something like what you see here. This is the equipment we have, or the old equipment. Locust and lumbering. We just received a new one. We bought it almost like 5 or 6 years ago before I got to my PhD. That's the operators, an arm attached to a wall or something. And there is a spring. So it goes down or up based on an increase in density of the subsurface. And I'm measuring what kind of G in this case? Relative. I'm measuring the relative change. So one thing, since I'm trying to measure vertical change, let's assume this is the apparatus and that's the surface of the earth. It's placed something like that. Is it fine to take measurement then? This is the apparatus. يعني هذا اللاين هذا الخط أنا آخذ الميجرمنت هذا الخط مايل شوية هذا البودي is no. So you need to level it properly. You need to level your apparatus really highly precisely. In this one, which was manual leveling, it took us sometimes even half an hour. أنا خليت طالب معي أول ما توظفتني في الجامعة الحين هو ما شاء الله شيخ عنده عقارات مع عقارات. أيوة أنا هني جالس الجامعة. جاء عندي مرة جاب لي رينج روفر خليل كيف أمورك؟ بعد جالس هني تعال معي بعطي 5000 بدل ما تشتغل هني. هي left even geophysics يعني ولا جيولوجي؟ ها؟ كيف؟ لا هو كان ما شاء الله شغول، كان فترة من فترات رئيس الجامعة، وكان فترة يوم كان يشتغل هنا في الجامعة كان عنده بزنس، كان يشتغل، كان عارف البزنس مرة، وراح اشتغل في شلمبرجر فترة، طلع معهم قال له ايش الفائدة هني؟ اخذ 2000 3000 احسن لي اسوي شركة بنفسي. ايوه ووظف معاه واحد كان جيوفيزيكس نفس الشيء، حد يكمل ماجستير، حد بيكمل ماجستير هنا معنا، عاد الايلتس 5 مرات. حاول مرة ثانية، حاول وظفوه في مركز رصد الزلازل، كان يستلم على 1100 1200، فهذاك وظفه معاه، قال تعال نوظفك معاي، فهم من عند السالفة كيف الشغل، قال مع السلامة افتح لي شركة. الحين يبيع أراضي، ما أراضي صغيرة، لا مناطق كاملة يعني ماخذ. ايه يقول لي خليل انا سافرت كان بريطانيا، جاء عندي مرة يقول لي تعرف كم خسرت؟ 100,000 خلال اسبوعين. 100,000 100,000 انا راتبي 10 سنوات. So I took that guy and we took almost 2 weeks measuring, doing measurement in SOAR. Nowadays CG5, the new equipment, you just put it down, it takes you almost like 2 minutes, 1 minute to level it. And in terms of measurement, gravity measurements is the easiest, fastest. One person can operate the equipment in comparison to like seismic reflection or seismic refraction or resistivity too. DC resistivity, they are quite tedious. We still have quarter an hour, so bear with me. We need to cover a lot. So we need to level it. It's a time consuming, it's very delicate, and whenever we measure we need to keep some distance. It has some remote control. You keep a distance, then press the remote control, start the measurements. So these are actually the corrections we apply. As I said, I'm interested in one part. I'm not interested in topographic change on the surface. I'm not interested in change on gravity value because there is tidal effects. I'm not interested because I'm measuring, today I'm measuring on the equator, tomorrow I'm measuring on the poles. These are not geological features. So we need to correct for these effects. One of the first one is drift. Then latitude, whether I'm measuring at the equator or at the poles. Then ITVOS, there is a correction, it's called ITVOS. What's ITVOS correction? It's the correction we apply if I'm taking measurement on a moving car. Not necessarily a car, I'm taking measurements while I'm not stationary. I'm on a plane. Nowadays they can take measurements while they are in, like, let's say a drone, to take cover bigger area, larger area in short time. So if you are taking measurements while the apparatus is not stationary, is moving, we apply what we call ITVOS corrections. Then topographic corrections, topographic change. I move the uphill, downhill, I'm in valley. And there are 3 different corrections. One of them is free air correction. The other one is Bouguer correction, and finally terrain corrections. These are different corrections I apply because these are non-geological. If I'm taking measurements on a drone, what do you think will happen to the gravity value? I'm away from the center of the earth. Will it increase or decrease? Decrease. That's free air. That's free air. What happens if I'm taking measurements while below me is a big mountain? That's called Bouguer. Because there is So let's assume that this is your reference point. That's a hill, and this is your reference point. This is your base station. You take measurement here. Next time you take measurement uphill. There is a rock right now, this big rock, which was not present here. So we apply what kind of correction? Bouguer correction. And there is also terrain correction. Original to residual corrections. For example, I'm interested in shallow chains, shallow surface chains, whereas there is a deep, the strata themselves, they are tilting. Those tilting strata, they will produce an overall, a regional change, whereas I'm interested in small change on the surface. So how to remove regional effect from residual? I'm interested in the residual small chains closer to the surface, whereas deep-seated features, they produce broader, large chains. So your anomaly might look something like that. If I draw the anomaly, you'll find it's tilting something like that, or making something even like that. Am I interested in this regional line or these small chains? I'm interested most of them in those small chains, not the regional. These are what we call residual, whereas the overall line is the regional. That's the corrections. It's not always applicable. We don't apply it quite all the time. We apply it sometimes. So next we explain each correction, how it's done next time. And you will have also a lab about these corrections. So we try to finish this part, explain how the corrections are done, then I give you a lab, explain the lab, you do the lab. So there are a few slides. Terrain correction, up until here, that's the residual corrections. Then we explain something about surveying, gravity surveying. So do you have any questions related to what we have covered today?